Um, Hello everyone. So this is my first video. In this one, I will discuss more about the history of cryptography and introductory history of cryptography, and then a detailed information on what is the standard encryption method and why is it the standard encryption method, and comparing it with other encryption method to see how efficient it is. So right now we will talk more about the history. So cryptography is the study of secure communication methods, right? So it's the study of secure communication method that only allows the sender and the intended recipient of a message to read its content. So it's not any recipient, it's the recipient that you would like to receive the message. So that's basically what cryptography is. That's just the term, and the derivation of the term is from a Greek word called cryptos, which means hidden, and the word hidden is very similar to encryption, because in hidden, when you hide something, you make it so that others can't see it, and in encryption it's the same thing. So in encryption, even though you can see it, you wouldn't understand it. So it's basically encryption is basically the process of scrambling a plain text. So it could be hello, how are you, into a ciphertext. So ciphertext is basically the jumbled words, you could say. So in a jumbled word paper, they might give you a word, and then you would have to rearrange them appropriately. And ciphertext is similar to that, but it's a bit more very advanced than what jumbled words are. And turning it back again, so turning the jumbled words back into the plain text is called decryption. So encryption is basically writing down the words and then you scrambling it, and decryption is the process of rearranging the words so that you get what the original message was. And this is the and I think the next 3 or 4 slides are going to be about the history of cryptography. So the earliest known example of cryptography was found in an Egyptian noble's tomb known as Kumhotep II. I'm sorry if I didn't spell his name right, I apologize. So this noble lived approximately 3,900 years ago. So it's very long, very long. In terms of, in comparison to a human life, it is of course very long. But this evidence, but the content that was in this tomb was not to hide anything special. It was just to make it appear more prestige or more enhance what it means. So for example, there are different types of English, such as the basic English or the Royal English, or like the first class English accent, or more advanced English. So just like that, this Egyptian noble had his tomb be engraved with these advanced symbols, and we kind of misinterpreted this as something hidden, but it wasn't really anything about that. But still, it kind of is at least this is one of the evidence that cryptography existed that long ago. And another known example is this one. So this was used by this was found in an Mesopotamian scribe to conceal a formula for pottery glaze. And this example is used was actually actively used to protect sensitive information during that time, right? So what they did was they would have their secret formulas. In earlier days, we had pottery as one of the main jobs. So everybody had their own secret recipe or the formula to make a good one. And this Mesopotamian scribe, I'm sorry if I spelled that name wrong, used cryptography to hide the information so that only their students or their mentors could read that, or their descendants could read that. So this is the more defined, or this is a more absolute example of cryptography being used, or a more confident example. We are more confident that this is an example of cryptography being used here. And another one is that another one was found in the Greek state called Sparta. So in this Greek state, Greeks used to write encrypt their messages in a paper. So what they would do is that they would write the message in a paper that is rolled around a cylinder, right? So they will have a cylinder, and they will wrap these small papers around it, or like the cutted papers, or like an horizontally long paper around it, and then they will write down their message so that only those who have the cylinder of a similar size can read it. And this is not a very secure, but at that time I would say this was a quite secure communication, because it would take long periods of time to make a cylinder similar to that size. But I'm sure they probably had many small letters so that it would confuse them. But yeah, we are not going to go deep in this, but this is just an introductory history. Another a more advanced type of cryptography was invented by Romans, known as Caesar cipher. So what this cipher would do is that it would shift all the alphabets, all the letters by 3. So A would become D, B would become E, C would become F, D would become G, and so on. If you really think about it, at that time, I would say this would definitely sound confusing to others, but it should be quite decryptable if they put in enough effort to decrypt it. This is still used by some newspaper groups or in internet to make a joke that they explicitly can't, or something that would endanger their business or something. But just to keep it fun, or maybe like a more exciting thingy, they would use this a Roth 13 algorithm, which is basically a shift of 13 letters in the alphabet. So A would be shifted by 13 letters, B would be shifted by 13 letters, and they will write down the word, and they would shift each corresponding letter 13 by 13, and you would write down the cipher text, which is basically the resulting text after 13 shift, to make a joke. So this would be so you can't bring this to a court and say, hey, this guy made a joke about me, and see, if I decrypt this like this, if I decrypt the message, then you could see what the joke was. So you can't really do that, right? Even though the court might realize that this was intended to be like an insulting joke, but they can't really do anything about a Roth 13 joke, majority of the time at least. Another major breakthrough in cryptography was made by Thomas Jefferson in 1975. His invention was the cipher wheel, also known as Jefferson disk. So in this wheel, you would have lots of ring in it, and it would basically act like an bit lock. And of course, each wheel will have 26 alphabets. And if you approximate, if you match it accurately, if you match it precisely as it was when they made it, then you would be able to decrypt the message, or maybe you could open something, or some space will be opened in that wheel, and you could kind of get the paper from it, something like that. Yeah, I mean, there were different forms like this, but this just shows that the cryptography was still relevant during that time. This is more of an earlier example, right? So yeah. Also, this was made in 1795, not 1975. I kind of made a typo, so I apologize for this, a typing mistake. But yeah. And then another latest example is going to be the Enigma. So Enigma was used by the Axis power, mainly the Germans, to send messages to various camps or stationed troops, so that they could coordinately attack or retreat without making a mess or be more organized. So they still used the similar concept of the Jefferson disk. As you can see, well, while it's not visually similar, it did have a similar concept being used inside it. So to decode this, you would need a specific word, that a word or a key that the German troops or the German commander gives, and it would change every single day. So it was quite impossible to do it at that time. But Alan Turing, so he and his crew, he was a major contributor, so that's why I have him. So he and his crew leveraged the new computers being made to successfully break the Enigma code, and this helped. This is one of the main factors which helped the Allied victory. And as computer technologies and computation power improved, cryptography became more advanced than it was during the analog era. So yeah, now we are pretty advanced than it was when the Jefferson disk was made. The 128-bit encryption is now the standard for many sensitive devices and computer systems. So for example, even your text messages could be encrypted in 128 encryption, in 128-bit encryption. Yeah, so that's why I think this is a relevant topic to be discussed about, because this could help you actually sound smart. And not just in messages and to encrypt text. Cryptography has also been used in many cryptocurrency, various advanced cryptographic techniques such as hash functions, public key cryptography, and digital signature are used to ensure the security of data stored on blockchains and to authenticate transactions. So yeah, as you can see, it's cryptography is still everywhere. As long as there is data, there is going to be cryptography with it. You could use cryptography in it. So yeah. Over the past 4,000 years, cryptography has kept on evolving, just like we saw in the future of cryptography. So basically, in the future, we would have more data for like the AI and other things, and to make sure they are safe, people would need to use cryptography techniques, advanced algorithms, and as our computers get more advanced, we would be able to break codes, but probably not the 128 standard, because with our current technology, it's quite not possible to break that code for an average person to do it. So yeah, cryptography will definitely improve, but it's gonna go more steadily. It's not gonna go into spike, because 128 algorithm is already very secure. So it's unlikely that we are going to see improvements. Well, we will see improvements, but it's going to be in a more steady phase. Now we will talk about the advanced. So before we talk about the advanced encryption algorithm, I just wanted to mention the difference between symmetric and asymmetric encryption, because what we are talking about, the 128-bit, is going to be an symmetric encryption, right? So symmetric encryption, just like the name implies, symmetric encryption is basically using one key for encryption and decryption, while asymmetric encryption is using two different keys, one for encryption, another for decryption. So key 1 can be used for encryption, key 2 can be used for decryption, but key 2 cannot be used to encrypt the data, or the other way around for key 1. Yeah. And symmetric key is also called a secret key or private key encryption, because it's kept very secure, very secure. Asymmetric key is more known as the public key or conventional cryptographic system, because even with one key you seriously cannot decode the message. So let's say you have the encryption key, and so in an asymmetric encryption, let's say you get the encryption key and you have the encryption message, and you want to decrypt it by understanding how the encryption key works. You still won't be able to do it. You need the decryption key to do it. So it's quite not possible to do it. Symmetric key is faster than asymmetric, because it uses same key, obviously, and it's also more computationally, it also uses less resource computationally to encrypt a message than the asymmetric key encryption. Yeah. And you might be wondering, why is it that same key is more faster than two different keys? And the reason is that there is less complexity in it, because you have the same key. You can understand both decryption and encryption at the same time if you just go through it, while for the asymmetric you need to understand encryption separately, decryption separately, and it would take a lot of time for it. So that's why asymmetric encryption is more faster and less resource consuming than asymmetric encryption. To encrypt larger messages, it's very conventional to use symmetric encryption, because plain text and ciphertext are treated as blocks of binary data, while in asymmetric encryption, plain text and ciphertext are treated as integer numbers, and you would need to do a lot of math, and yeah, it's not feasible to do asymmetric encryption. So you might be wondering where we use asymmetric encryption, while majority of the things, so small text, so let's say you're texting somebody, it's probably not going to be a military grade information, right? It's not going to be a national, your nation's not going to be at risk if when you're texting somebody, maybe you might say hi. That's not a national threat level information. So for that you don't need asymmetric, you just need some symmetric encryption method. And while you take military, for example, they might have large continuous larger amount of messages, because you will need to constantly communicate with your peers to effectively engage in a battle. So for that, asymmetric is not very useful because it's more resource consuming and less productive than symmetric. So what we would do is that we would use asymmetric encryption to encrypt the symmetric key and use the symmetric key to encrypt the message, to decrypt or encrypt the message. So asymmetric encryption is used to secure the symmetric key, and the symmetric keys will be used to encrypt or decrypt the message. So as you can see, we don't use it directly, we just use it like this. Majority of the time we use it like this. Some of the algorithm example for symmetric encryption is going to be DES, AES and Blowfish. We will, in this presentation, we will talk about AES. Yeah, so again, some examples for symmetric encryption are DES, AES and Blowfish, while some of the example for asymmetric encryption are RSA and Diffie-Hellman key exchange. Of course, there are many other encryption algorithms that or models that are available, but these are some of the more popular model or more influential model. And out of this, the AES is the most influential, or it's the standard one. That's why it's more influential. It's used in majority of the places where you need to encrypt data. So yeah. And now for symmetric encryption, this is how it's represented. For asymmetric encryption, this is how it's represented. I will explain what this what this actually means in just a minute. Right. So this symmetric encryption, with this mathematical representation of the symmetric encryption, basically means that the cipher text is generated by encrypting. So C for ciphertext, E for encryption. So ciphertext is generated by encrypting the plain data P with the key K. Okay, so that's how you get ciphertext. Obviously, yeah, obviously that's how you get ciphertext. But yeah, for ciphertext, you would encrypt the plain text with the key. Okay, and to get the plain text, you would decrypt. So D for decrypt. So you would decrypt the ciphertext with the key, with the same key. Yes, of course, with the same key. Yeah, because it's symmetric encryption and they both use the same key. That's what the mathematical representation of the symmetric encryption mean. Okay, so now we will talk about the asymmetric encryption. Yeah, so the mathematical representation for asymmetric encryption is represented as this. Sorry, I have a few network issues, so it's kind of like that. But yeah. So to get the ciphertext, you would encrypt the public key of the sender with the plain text, and to get the plain text, you would decrypt the private key of the receiver with the ciphertext. Okay, sorry, my bad. So to get the ciphertext, you would basically encrypt the plain text with the receiver's public key. So PU, R, is the public key of the receiver, P is the plain text, and is the encryption. Obviously, sorry, I made a small wording mistake. So yeah, so to get the ciphertext, you would encrypt the plain text with the public key of the receiver, and to get the plain text, you would decrypt the ciphertext with the private key of the receiver. So yeah, that's basically how the mathematical representation of the asymmetric encryption means. What the asymmetric encryption mathematical representation means. Yeah. Now we're going to talk about the importance of cryptography in modern systems. Ciphertext is the resulting combination of letters after doing an encryption. Alright, so yeah, that's what we mentioned before. I mentioned before. So yeah, encryption is basically taking a set of words or a sentence and following a set of rules to scramble the letters of those words. So in basically encryption, you would take a word or a sentence and then you would follow a set of rules to scramble the letter of those words. To encrypt a message, we usually need a cipher, the cipher, and a key. Cipher tells us what rules are needed to be followed to encrypt or decrypt words, while the key allows us to apply those rules in a logical manner following the cipher. Cipher and ciphertext is different. So in this one, cipher, we are talking about the rules. You can assume cipher has rules, while ciphertext is the resulting text after we follow those rules. Cipher is the rules that we follow. So yeah, cipher are the rules and key allows us to use them in the logical manner. So you could say cipher is like rules in a jumbled order, while key just arranges it like 1, 2, 3, 4, 5 accordingly, sequentially, or however it's supposed to work. And there are two types of cipher. So Roth-13 algorithm is the example of a monoalphabetic cipher. Each letter of the alphabet is assigned to another letter consistently through the whole text. So what this basically means is that F might be replaced with G, and in the entire sentence or the word, F will be replaced by G and not by any other letter. So it's pretty easy to decrypt this because it's monoalphabetic. The replacement is consistent, so it's a function. Basically, it's a proper function for one input. We have one output. So similar to that, for one word, we would only have one changeable word. So A will only be replaced by B, or maybe B will only be replaced by A. So yeah, that's what a monoalphabetic cipher means. You would replace all the letters in a word or a sentence with the same letter. And so since this is not effective, or this is pretty easy to decrypt, we need more advanced type of cipher. So we have polyalphabetic cipher. So this kind of cipher can substitute multiple different letters to a single letter. So in a sentence, A might be replaced as B, and it could also be replaced as C, or maybe additionally even D. So as you can see, you can replace one word with all the other words. So it's more secure because it's less straightforward. You would have to do a lot of things to get the intended message, the message sent to the intended recipient, to decrypt that message. You would need to do a lot of things. So yeah, that's why this is more advanced, and this is also used in the standard encryption method. And in a polyalphabetic cipher, the key is usually a word rather than a number. So yeah, and of course this makes this cipher much harder to take out than a monoalphabetic cipher. Now we're going to talk about the basics of Advanced Encryption Standard. AES, also known as Advanced Encryption Standard, was published by NIST National Institute of Science Technologies in the year 2001. This is a powerful alternative to DES, which is not a secure encryption standard. I will explain why this is not secure and why AES is more secure than DES. So AES is a symmetric block cipher, same key used for both encryption and decryption. AES is not only a symmetric cipher, it is also a block cipher, right? So remember, it's not just a symmetric cipher, it's also a block cipher. Block cipher takes a group of bits as the input and produces a group of bits as the output. So when we talk about how AES encrypts its message, you will notice that it's going to take bits, a group of bits, instead of maybe one each bit by bit, or the alternative way. And that's obviously what the word block cipher means. Block, you could assume it as a group, and cipher is basically like the rules to scramble a data, right? So those are the rules. So that's cipher means the rules, and you could assume block as like set of data. Obviously, I think you understand what I'm trying to say. Block cipher takes a group of bits instead of individual or all. So yeah, instead of taking one bit or one byte at a time, it rather takes a group of bits. Yeah, that's what we mentioned before. To be more precise, it's going to take 128 bits as the input, plain text size, and 128 bits as the output, ciphertext. Because of the many powerful feature in AES is widely used even in today's world. Yeah, of course, it will continue to be the standard algorithm for the maybe the next few decades probably. Yeah. Until we humans could have supercomputer on our hand, it's probably unlikely that AES will be broken. But yeah, so when I mention it's going to take 128 bits as the input and 128 bits as the output, this is for AES 128. So there are different types of AES, and we will go through them. But AES 128 is the standard. AES is the standard, but AES 128 is more widely spread, so that's why we say AES 128 is the standard. So yeah, so this is the structure of the advanced encryption algorithm. In AES, the plain text and the ciphertext will always be of 16 bytes or 128 bits. This ensures that no data is lost or added during the encryption or decryption. The input, basically the plain text, is arranged into a input state array which is of 4x4 or 16 bytes to make processing easier. So basically the plain text, which is of 16 bytes or 128 bits, will be put into a state array which is also of 16 bytes to make processing easier. So how does this make processing easier? Because if it's a state array, then we can perform the specific math concepts easily. So for this algorithm, you have we will use many matrix multiplication and other similar things, and for that, having an input as an array will make it so much more easier, or as a matrix will make it so much easier. That's why we make it into an input state array, and then we will perform an initial transformation in this input state array using the round 0 key, and then the output of the initial transformation is given to round 1, where we will perform round 1 operation with round 1 key. So basically the input state, which is of 16 bytes, is performed an operation using the round 1 key, which is the initial transformation. The result of the initial transformation is the state after initial transformation, which is also of 16 bytes. So no data is added or lost. This thing basically scrambles the data to keep it more secure just for the initial transformation. Then the output, which is basically the state after initial transformation, is given to round 1, where we will perform the operation using the round 1 key. Then the output of the round 1 is given to round 2, where we will perform certain operations using the round 2 key. So this goes on and on and on till the round before the last one. So why do I mention the round before the last one instead of the last round? Well, this is because the round before the last one, or n-1, has 4 transformations. So basically the round n-1 has 4 transformations, and it will perform this transformation using the round n-1 key, which is of 16 bytes. Then the output of the n-1 round will be given to round n, where we will perform 3 operations. We will perform 3 transformations using the round n key. Now this might seem a bit confusing, but just know that the input state, which is of 16 bytes, will perform an initial transformation. Then the output will be given to as the input as for round 1. Then the output of round 1 will be given as the input for round 2, and so on and on till the last round. But the first transformation performs only 1 transformation, while round 1 performs 4 transformation, and every round except the last one performs 4 transformation. Then the last round performs 3 transformations, and for each of these transformation you would need a specific round key for it, and each of these round key are predefined, and they are 16 bytes in nature. They will not change regardless of the variation we have in the AES. Now I will mention what these variations are shortly, but just know that the round key will always have 16 bytes as its size. And what happens after the final round? You will give the output of the final round as the final state array. Then that's where we get the ciphertext. We will basically convert this array into a text, then we will get the ciphertext. So how do we know how many rounds there are, and what is this? So how do you know what this is and how many rounds we have, because it's mentioned as n rounds? Well, basically AES has 3 variations, which is AES 128, 192 and 256. So these are the 3 variations. In AES 128, the key size is 1 to 8. So it's same to as what the name is here. And in AES 192, the key size is 192. And in AES 256, the key size is 256. So before getting confused about what the difference between key size and round key sizes, key size is basically the original key that we use to begin the encryption, and the round key size is the key that we expand upon based on the original key using this key expansion algorithm to perform each round. So you will have an original key, and then you will use the key expansion algorithm to expand the original key into various key so that you can perform the round 0, round 1, round n-1 and round n. So these are the round keys, which is right here, and as I said, they are all 128 bits or 16 bytes, and the key size differs. That's why we have it as a variable. The plain text size, again like I mentioned, the plain text and the ciphertext size will remain same, and cryptographers have found the optimal number of rounds you have to perform to keep it safe. So you could just follow this, or you could add upon them to keep it more safe, but it's gonna be more costly in terms of computational power. But you could of course use as many rounds as possible, but this is the rounds that people use predominantly. So yeah. So this is the AES encryption and decryption diagram, and this diagram will allow us to understand what is happening in each of the round inside. As we have studied earlier, the plain text and ciphertext will be of 16 bytes, and they are constants, so they are predefined in all the AES variations. Now this is a diagram of AES 128. That's why we have 10 rounds overall. So our first transformation was an initial transformation, and this is what we see here. This is the initial transformation at round key. This is what happens inside the initial transformation, and this is the initial transformation basically. And after this initial transformation, the output is given to round 1, where substitute bytes, shift rows, mix column, and add round key transformations take place. Again, so in each round we have 4 transformation, and they are substitute bytes, shift rows, mix column, and add round key. So in the first transformation we will perform and add round key transformation. Then with the output we will send it to round 1 as the input and perform these 4 operations. Now I have mentioned that since it's an AES 128, we would need 10 rounds and we would have 10 round keys. We actually need 11 round keys. Well, yes, we need 10 round keys. So for round 1 we need its own round key, and for round 10 we need its own round key. So, and in between 2. So for each round we need its corresponding round keys. And aside from those, we need an additional round key for the initial transformation. And what are these keys, you might be wondering, right? So since a word is of 4 bytes and 4 bytes is 32 bits, and 4 words will be 16 bytes and 16 byte will be 128 bits, and that is our round key size. I have made a typo here. It should be 4 words, 16 bytes equals 128 bits. But for now let's just pretend that this is 4 words and 16 bytes instead. So we know that the key is of 16 bytes, which means all of its subkeys is also going to be 16 bytes. And what makes this 16 bytes up, like what is inside these 16 bytes? There's going to be 4 words, and make sure you remember that this is an closed bracket or a square bracket, which means the value are included, the 0 and 3 are included. So it's not 1 and 2, it's 0, 1, 2, 3. So the words 0, 1, 2 and 3 are the key for the first transformation. Then the word 4, 5, 6 and 7 are the key for the first round, and it's gonna go on and on till around 10. So in round 10 the words 40, 41, 42 and 43 are the key for round 10. Now this is the side of encryption. We will talk more about these transformations later on, but just again remember that round 1 to round 9 or round 1 to round n-1 will have 4 transformations, while round 10 or round n will only have 3 transformation, where mix column is not there. We will talk more about why it's not there and why other things are there later in the shortly, or later down our path. And as you can see, if you add all these keys up, you're gonna get 44 words, and that is actually the requirement for AES 128. And if we have a different AES variation, for example AES 192, we would need 52 words, and if it's AES 256 we would need 60 words. So that's our requirement list. And what are these words actually? Well, these words are actually bytes of information that are supplied from the initial round for transformation. So all these all these around keywords are bytes of information, 4 bytes of information, because it's 0, 1, 2 and 3. And in the decryption side, it's actually not the opposite you would expect in a what you would expect in a typical cryptography setting is that you would need to do the opposite to achieve your initial message or the encrypted message, but it's quite the opposite here. What you will do is that you will use the last 4 words, but you would keep the round process the same. So you would use words 40 to 43 for the initial round, and you would use the last 4 words before these 4 words as the key for round 1. So as you can see, this is the words that we use for round 9 and round 1, and it's actually quite the contrary to what you would expect. It's just that the words are flipped upside down for us. The words are flipped upside down for the keys. And even in this one, as you can see, we don't have mixed columns, and you could notice the names that it says inverse shift rows, inverse subbytes, inverse mixed columns, and all these transformations. But add round key is just add round key and not inverse add round key or something like that. I will explain why it's not like that later on. If you have no idea on what the add around key is, I will explain it. So yeah, and that's basically what the diagram is even about. There's really nothing here. So the plain text 16 bytes, ciphertext 16 byte, data kept same, and the plain text takes the word 0 to 3 included for initial round, and the next 4 words for round 1 and next 4 words for round 2, and so on till around 10, the last 4 words. That's basically how we get the ciphertext. And to convert the ciphertext back into the plain text, you would use the last 4 words for the for the initial transformation, and you would use the last 4 words before the last 4 words. You would use the 4 words before the last 4 words as the key for round 1, and so on and on and on. That's basically all we have in this diagram. And now we will talk more about the different transformations. We will do a much more comprehensive review on what these transformations are and what they do in these slides. Alright, I kind of added the name here just to make it so that you guys can keep track of where we are. So this is going to be the key expansion or the key scheduling, what's happening in this part of the structure. We're going to look at what's happening in this part of the structure. Okay, so a quick overview. This is the graph or the words that each key use, and it is what we are going to study more about. Yeah, so we are basically going to study what happens like in each of the transformation, even in more depth. So I mentioned that we will go through these later on in the video, and that's what we are precisely going to do. This chart is just an overview, like I mentioned, how we have words 0, 2, 3 with 0 and 3 included. So those are the words or bytes of information that is stored in each key. And this chart just shows what words are in each round, like an example chart, just for us to refer, so that I don't have to go backward and forward for us to go through this. So as you can see, the initial transformation uses word W, word 0, word 1, word 2 and word 3 as the byte information byte on the initial transformation, and on round 1 it will use the next 4, which is basically 4, 5, 6 and 7 and so on till 44. So yeah, right. So if you remember, I mentioned that we are taking a look at the AES 128 structure. So in this structure we will have 10 rounds. So in the last round we will have 3 transformation, while in the first round, and then the n-1 or the 9th round we will have 4 transformations. So now we will take a look at the example of an round which has 4 transformation. So this is our input state array, and this is now given to subbytes. So what happens here is that a substitution or a table lookup sort of thing is going to be performed here. Again, we will go even more deep into this. Like I mentioned, we are going to take a look at this part, not the transformation yet, not just yet. We will take a look at we are taking a look at this part. So we are going to be talking more about the key expansion, and for that we need to know what these are. So that's why I'm kind of introducing this to you, but you should be able to understand what is going on based on what I'm saying, because this is really easy stuff. This part is really easy. So in subbytes, basically substitution is being performed here. So this is the S box, substitution box, and then we will perform substitution by looking up the contents in the input table on this and then getting the output. And this output is going to be given to shift rows, where the first row is untouched and then the second row is performed at 1 byte left circular shift, and then the third row is performed with 2 byte left circular shift, and then the fourth row is performed with 3 byte left circular shift. So in the shift rows, it's really simple. First row you keep it untouched. So this row, the first one, you will keep it untouched, you will not touch it. In the second one, you will move each content to the left by 1 byte. In the third one, you will move each byte to the left by 2. So that's 2 byte left circular shift. And in the fourth one, you will perform a 3 byte left circular shift. So that's basically what happening in the shift rows. Really simple. And then we will get an output, and then this output is given to mix column, where a basic a very simple matrix multiplication is carried out. So this is a predefined matrix, and this is also predefined, the S box, the substitution box, and then this matrix that we are multiplying our output of shift rows. So this is predefined. So we will multiply this with this. So as you can see, this is 4 times 4, this is also 4 times 4, so it's going to give us a 4 times 4 output. And then this output is going to be added with the round key. Adding with the round key means a basic XOR operation is being carried out. Now I'm not really sure if my viewers know what an XOR operation means, which I will just explain once I finish explaining this. I'm pretty sure you will be able to understand it even after I explain the whole thing. So yeah, and then after performing the XOR operation, you will get a state matrix at the end of the round. Now as you can see, this is mentioned as variable input. Of course this is a variable input because for our round key is of the same size, but our contents or the information inside it is different, right? So for each round you will use different words, different 4 set of words. So our output is going to be very different because our round key is different. But if you had the same round key, then you will see the same output for 2 rounds, I would assume. And that's pretty much what's being mentioned here, I believe. Yeah, and that's it for that diagram. Now we will move on to the next one, which is basically talking about the G function that I will explain in a minute. Right, so now we will take a look at how the key is being expanded, how we generate the keys and other things, right? So I'm not sure if you remember this, but one word has 4 bytes in it, and you can assume each of these boxes as 1 byte, right? So you will assume K0 as 1 byte, K1 as 1 byte, K2 as 1 byte, and K3 as 1 byte. So like that, you will have a 4x4 matrix which equals 16 byte, which is the same as 128 bit, and that matches our initial data size. So what you will do is that you will add the columns of this matrix, so like each column of this matrix, and it will give you a word, because 4 byte combined will generate you a word. So if I add K0, K1, K2 and K3, I will get W0. Likewise the same for this column, and this column. So if we do all of that, then we will get W0, W1, W2 and W3. Now we can use this for the, there you go, the initial transformation. We are ready to use this key for the initial transformation. But the thing is, we need 44 words, right? So to get that, we would have to use the G function. But I'm not gonna, I'm not sure if I mentioned this, but I'm not gonna go deep into this right now, not now, but just after I finish explaining what's going on here, I will explain what's going on here. So now we have all these words. We are ready to use this for the G function. As you can see, this is W0, W1, W2, W3 that we use here. For the initial transformation, we will use W0, W1, W2 and W3. So we have the requirements. We have met the requirements to perform the initial transformation. So now we will take W3 or the last word. Then we will put this into the G function. So we will put it here, and then we will get an output, which is the W dash. We will assume, or since we don't have a specified input, we will just assume it as W dash. So we will get this W dash, and we will perform an XOR operation with the W0 word. So when we add this and this, we will get this again. So we have W3, we will put this into the G function. So G of W3 will give us an output, that is W dash, and the output is performed XOR with the W0 or W0 to give us a result of W4. So this will generate a new word for us. This process will generate a new word for us. Again, W3 is given to this function, and it will do the process, and you will get an output, that is W dash, and you will perform an XOR with this output and this initial value or W0 to get the next word, which is W4. Now you can't do the same thing for W4. What you have to do is you have to perform XOR with this W4 and W1 to get W5, and you will do the same thing to get W6. So you will perform XOR of W5 and W2 to get W6. Now you will get the W6 and perform an XOR with W3 to get W7. And now how do you generate the next 4 words? Obviously it's going to be the same thing. So you will put the W7 into the the G function, and then you will get a result, which is W dash, and then you will perform an XOR with the W4 to get W8, and it goes on and like that till we reach our word limit. Now as you can see, this will allow us to do the round 1. So for round 1 we need W4, W5, W6 and W7, and this exactly lets us perform or do all of that. Now let us take a look at what's happening inside the G function. So let's say we have W3, we will put the W3 here, and as I mentioned earlier, since one word equals 4 byte, we will separate this one word into 4 different parts, which is going to be B0, which is byte 0, byte 1, byte 2, byte 3. Then our first step is to perform an one byte left circular shift. So we will move the W3 1 byte to the left. So this will go over here, which is what we see. This will go over here, which is what we see. This will go over here, which is exactly what we see, and this will go, well, there is no other place, so we will go backward and we will end up here. So as you can see, this is the one byte left circular shift that I mentioned happens over here in the shift rows. So yeah, the what's happening in the shift rows is very similar to what's happening here. So yeah, now you actually have an overview of what's going on in the shift rows. So like when I mentioned the 1 byte, 2 byte, 3 byte left circular shift, this is exactly what I'm talking about. But in this one, we are only performing one byte left circular shift. So now we have all these words. We will then use an S-box, not an Xbox. We will perform we will find the value that can be substituted instead of this. So basically, okay, how about this? I will give you an example. So let's say this value is 75. Let's say this value is 75. Okay, this is the S-box, right? So this is the S-box. Now all of these things, they are in hexadecimal. So like it will be from 0 to F and 0 to F. So these are in hexadecimal. So this is our, so we are taking this byte as an example, right? So this byte is 75. Let's say this byte is 75. We will look for 7 and 5. 7, let's see, 7 and 5. Where does it intersect? Okay, 5, 5, 5, 7. Okay, there you go, 90. So it intersects at 90. So if this was 75, then after performing an S-box, it will be replaced by 90. Similar to that, whatever value these three have, after performing an S-box, it will be replaced by the appropriate value. Now we will perform an XOR with these values. So these three are constants, 0, 0, 0, they are constant, they won't change. And RC, it's very similar to what the name says, it's just the round constant. Round constant is just a constant that you have for each round. So for if this was for round 1, so let's say if this was for the round 1, if the G function is for the round 1, then you will use the round constant for round 1, which is 0, 1, as you can see, 1. So this will be replaced by 1, and you will perform an XOR. So you will perform an XOR between these two, with these two. Then it will produce you the result W3 dash. So that's exactly what's happening in G function. Again, for round 0, you will have 0 as the base, and for round 1, round 2, round 3, and so on and on and on, you will have this specific value as your round constant. So you will just get the first value, so 20, take that. Let's say you're in, so let's say you're in round 6, take the 20, and you will keep it here, perform an XOR between these two, then you will get the dashed value, or the W3 dashed, because we put W3 as the input. Then you will perform an XOR with W0 to get W4. That's exactly what's happening here. This is very simple. If you don't understand it, maybe try watching it again, or by just looking at the diagram, take a minute, look at the diagram, what's happening here, then you will understand. That's basically what we all have here. Okay, so now we have gone over the key expansion process. Now we will talk about each of these substitution process. I believe we have gone over the subbytes. No, sorry, that was S-box. Okay, so we will go over all of these substitution process, which is the substitute bytes, shift rows, mix column, and add round key. So we will go in depth on each one of them, and then we will go in depth on each one of them and then discuss more about it. Another important note, all encryption algorithm must have two important steps, which is confusion and diffusion. All the four transformation above provide the confusion and diffusion properties to the encryption algorithm. So as you can see, substitute bytes or subbytes, just like the name says, it is a substitution property. Then shift rows is a permutation property, so position of the letters are changed. By the way, if you don't know the difference between substitution and permutation, it's right up there. So permutation is the action of changing an arrangement. Substitution is the action of replacing something with another thing. So substitute bytes or sub bytes is basically replacing, just like the name says. So that's why it's substitution. And in shift rows, you're changing the arrangement. You're moving it by one circular to the left, 1 byte. So you're performing in 1 byte circular shift, 2 byte circular shift, and an untouched at the initial. So they are changing the order. So that's why this is called permutation. And we have mixed column. This is not in the last round, just for a reminder. I'm sure I said this already, but this is not in the last round. So in mixed column, it's basically a substitution, because you're mixing the column. You're mixing the column to generate new value. And we have add round key. Add round key, I'm sure I'm not really sure if I explained this, but we have gone over. We have seen add round key in many of our cases, such as the initial transformation. We have add round key, and in the last transformation of any round is basically add round key. So this is a substitution. You will perform an XOR with the round key value. So with the input, you will perform an XOR with the input and the round key value, which will provide a new value. So it's basically replacing some, getting two things and then gaining a new thing. It kind of goes into substitution, even though some people might be confused on why this is substitution. It's generating a new value. It's not substituting anything, right? But it's because it's substituting the input value with another value using the round key as an support or aid. So it kind of goes into the substitution category. But you just know that, I mean, even though you don't assume this is substitution, we still have substitution, permutation, and substitution here. And all of these things are included in the property of confusion and diffusion. So all of these four things go through confusion and make the data confuse and diffuse. So that's how this AES algorithm is being kept safe. Now we will go deeper into what the substitution bytes are basically. So substitution byte is basically a lookup table. So each value in the matrix will be replaced by the corresponding value in the dash matrix by merely looking up the substitution table. So let's say you have S5. You will try to look the value of S5. Okay, so we went over this, right? So yeah, assuming the value is 65. Okay, so let's take 21 for example. If it's 21, you will go to 2. Okay, let's say, assuming this is 2, it's kind of very small. Assume this is 2, and so you will find the x and y coordinate for it. Assume this is 2, this is as 1. Then you will find the intersection of that. Then that will replace the appropriate value. So S5 will become S dash. Whatever the input is, you will find the x and y coordinate of it, get the intersection, and replace it. So if it was 36, you will then separate 3 and then 6, find the intersection, then you will get the substitute. 3 is going to be the x, 6 is going to be the y. That's how it works. Okay, and this is the shift rows. This is what I said. So the first row remains untouched. As you can see, the first rows, nothing is being performed here. And in the second row, exactly, so we are performing in 1 byte left circular shift. So we are shifting it by one place exactly. There you go. So you see, take this value. This value will go over here. This value will go to left here. This value will go to left here. And well, this is the end of the box. So you will pull it forward because there's an empty space here. So we will perform in 2 byte left circular shift. So this box will go to left 2 steps. So let's see, 1, 2, and then this one will go 1, 2, this one will go 1 and then 2, this one will go 1 and then 2, this one will go 1 and then 2. So it keeps going on. It keeps going on and on. So that's basically what a 2-step circular shift is. Left 2 byte left circular shift is. and this is the 3 byte left circular shift. So as you can see, this one goes to the left 3 step, so 1 2 3, and then this one goes 1 2 and then 3. That's why we have the arrows over here. And then this one goes 1 2 and then 3. That's why we have the arrow like this. It's like a shortcut. So and then this one obviously goes 1 2 then 3. That's why we have the arrow like this. Well, that's basically what shift rows is. Very simple, very easy, straightforward. Now we have mixed columns. So in mixed columns, you will basically get the input and you will multiply it with a predefined table. So this is our predefined table. So this is also going to be 4x4 because our value is also 4x4, which is the input state array. And then you will get the output state array, which is also 4x4 because the matrix size is being preserved in the matrix multiplication. The input state array is multiplied with a predefined matrix. Okay, so that's what I have just mentioned here. And that's exactly what's happening here in mixed columns. You would basically just do a multiplication. You would basically just perform a multiplication. Yeah, that's basically it. Now if we kind of, let me just go back. Yeah, as you can see, new values are being produced and the previous value is being substituted. That's why mixed column is in substitution category. So we could see why it's in the substitution category. And now we have the add round keys. So in this one, a simple XOR operation is being carried out. We are getting 4 words for the round key from the key scheduling algorithm. Okay, so we will get the 4 words from the key scheduling algorithm. Take word 1, word 2, sorry, word 0, word 1, word 2 and word 3. For example, I is basically a placeholder. You can replace it with round 0. Yeah, I is basically the round. Let's take round 0. Round 0 key is used for initial transformation. So we will have word 0, word 1, word 2 and word 3. So these are the data given by the key scheduling algorithm. And then a simple bitwise XOR operation is carried out between the input matrix and the round key. The first column in the input matrix is XOR with the first value to produce the first column of the output matrix. So you will get these value, so S0, S1, S2 and S3, and you will perform an XOR with the W0 column to get S0 dash, S1 dash, S2 dash, S3 dash. Then you will take column 2 and then perform an XOR with the column 2 of this matrix to get this result in the output table, and you will do the same for column 3 with the column 3 in the round key, sorry, the word table, the word matrix, to get the output of the third column output for the output matrix. So yeah, again, adding the round key means a simple XOR operations. I'm pretty sure I mentioned this before, but yeah. This is just an overview again to do about what we just did. This might have been pretty fast because it's pretty easy, I believe. So yeah, again, permutation is the action of changing arrangements. Substitution is the act of replacing something. Subbyte or substitute byte, it falls under the substitution category. Shift rows is the permutation. Mixed columns is the substitution category. Add round key is the substitution category. Okay. Again, this is just an this was supposed to be an overview, but we will skip that. Okay. Now we have gone over what AES is. You now have an idea of how things work in the cryptographic world. So the things that we use in AES is pretty much used everywhere else. Of course, there's going to be few tweakings, or the process is going to be entirely different. But whatever we have discussed right now, the concepts are being used over other places too. Okay, so we're going to compare AES with the other two previous algorithms. So the first one, we had the DES. DES is basically the Digital Encryption Standard. So it's developed by IBM in 1970s. So it's originally So its original name is called Lucifer, and then NSA requested changes because DES was not very secure as computational power went on. I'm pretty sure I kind of mentioned where, okay, so yeah, as you can see, in 1998 DES message was cracked in 3 days, so it was very unsecure. And in 1999, just a year later, I think this was just a month difference, I think, or maybe a year difference. I'm not sure what the difference between this thing and this event and this event is. But in 1999, a network of 10,000 desktop systems cracked a DES encrypted message in less than a day, right? So this was becoming very unsecure, and the NSA requested to change it, but people thought they were trying making it so that they could read all the encrypted messages that is kept in companies and facilities or industries. So yeah, and then next, okay, oh yeah, let's go to this. So in DES we have 56-bit keys, so it's a block stripe cipher. It's not a stream cipher, so it's similar to AES. AES is an symmetric block cipher, I believe. So yeah, it is a symmetric block cipher. What am I even talking about? Okay, so in DES we use 64-bit blocks, and now we had this triple des, which is basically des performed 3 times. So this was still not unsecure, so this was just an escape code, or this was just a temporary solution so that NIST could propose a new stronger algorithm which was the AES. So they held competitions, or they did a lot of studies and comparison to see which was the best, and AES stood out, so they proposed AES. But before going into AES, of course we went over AES, but we will talk a bit more about the triple des. So in triple des, of course, the AES algorithm used 3 times, just the name implies. K1 is used to encrypt a message P, resulting in a C1 cipher. K2 is used to encrypt a message K2 is used to decrypt C1, resulting in C2 ciphertext. K3 is used to encrypt C2, resulting in C3 ciphertext. So this is kind of a process. So key 1 is used to encrypt a message, resulting in a ciphertext, and key 2 is used to decrypt the C1, resulting in a C2 ciphertext. And key 3 is used to encrypt the key 2 ciphertext, which results in a C3 ciphertext. So it's kind of like an encrypt, decrypt, encrypt process. This might sound confusing. The wording might sound confusing. So I would recommend you to research more about what this process is. I believe my wording is not correct, so you are getting confused, because if you decrypt this ciphertext, then you should get a plain text, not a ciphertext, right? So you might be getting confused by my wording or how I have written it here. So you might want to do just a bit research on this, because unfortunately my wording is not good, my grammar is not good. So yeah, and in this one, it's still using this block cipher with 56-bit keys, but it's just being performed 3 times. Everything else is basically the same. Applying 3 different keys yield effective key length of 1668 bits. So this was taking so much computational power. This was just not being effective. And then we will talk about AES. So NIST requested proposals, and in 2001 NIST published an algorithm called Reindoll as AES. So Reindoll specifies variable block size and key length multiple of 32 bits. Of course, that's exactly what we just went over. And AES specifies a fixed 128-bit block size, but key length of 128 192 and 256 bit. So we went over AES, but what we really went over is just the rain down, but it's in a more specific way, right? So rain down is the algorithm used in AES, but we don't use the 32 bits or the other things. We only have three variations, which is the 128, 192 and 256, because they are the most they perform very optimal in any scenarios. That's why we use these three variation only, and not any other 32-bit variation. But of course you can use it if you have enough computational power. You could actually use your own you could use rain down and have your own bit length, your very big round size and everything to keep it more secure. So as you can see, that's exactly what we have said here. A stream cipher is a type of encryption algorithm that encrypts plain text one bit or byte at a time, rather than encrypting data in a fixed size blocks like a block cipher. So yeah, this was just supposed to be a note to understand the difference between stream and a block cipher. So in a stream cipher, you will do it one by one, bit by bit, or in small pieces of one. So if you have if 5 numbers, then you will go like 1 and then 2 and then 3 and then 4. But in the block fixed size blocks, you will just get the entire thing and then encrypt it instead of doing it one by one. So why AES and where is it used? Yeah, so it was selected by NIST in 2001 to replace DES due to its superior security and efficiency. So that's just exactly what I mentioned in the previous slides. Nothing really new here. AES is well used in modern technology and applications for encrypting sensitive data. Examples include data protection, communication, wireless networks, mobile devices, financial transactions, cloud storage, and government and defense. Right, so this is exactly what we went over in the starting. Security of AES. AES is designed to be highly resistant to common cryptanalysis techniques such as linear and differential cryptanalysis due to its structure and design principles. Key features of a bit type: byte-oriented SPN. Okay. A lot of byte orientation, byte level operation allow for faster implementation in software and efficient hardware designs. So since AES is a byte level operation, right, so it mainly performs at byte level. It's very fast to implement and implement in the software and make good software designs, make the designs more efficient and be faster. So this will not provide any pain for your hardware. That's why we use AES. Byte orientation simplifies processing while ensuring robust security by operating on fixed 8 bits unit. Okay, then let's take a look at the benefits of SP in AES. Security, we have security, okay, combines confusion and diffusion effectively to thwart linear and differential cryptanalysis. Okay, efficiency, byte-oriented design aligns with modern hardware and software processing capabilities. Okay, scalability, easily adaptable to varying length and use cases. So this is exactly what I said. We could just use any key length. If you have enough computational power, you could actually use any key length and any of the variation, but it's unlikely that you would have to use any of that when there are lots of docs and lots of examples, and there is a huge, if the majority of them are using 128, 192 and 256, then I don't think there should be a reason for it to use anything other than that, because you don't have enough support for that and you will not be able to fix anything if something goes wrong. A byte-oriented substitution permutation network is a cryptographic structure that combines substitution blocks and permutation layers to achieve secure and efficient encryption. Okay, so this is exactly what we just mentioned before, except that I didn't mention that this is a byte-oriented substitution permutation network, or SPN. So all these things, as you can see, the key mixing, round-based structure, permutation, substitution, so those things fall under the byte-oriented SPN. Round keys are XOR with the state after substitution and permutation, ensuring that encryption depends on the secret key. Okay, resistance to cryptanalysis and resistance to differential analysis. So we will talk about, no, we are not going to go deep, we're just going to do an overview or just an 2-slide presentation of what they are. So cryptanalysis attempts to exploit linear relationships between plain text, ciphertext and key bits. So the relationships are going to be very linear, right? So in a linear function or in a linear line, if you have 2 points, then you could just pretty much figure out the entire graph. So let's say I give you a point of 0, 1 and 0, 3, then you will know what kind of line it is, right? So it's basically an x equals 0 linear equation. So I will know every other point if I just give you 2 points. So this is very unsecure or a vague function. Differential cryptanalysis studies how differences in plain text pair affects differences in ciphertext pairs, SBOX or subbytes, a non-linear substitution step that eliminates linear dependencies, right? So because we use XBOX, it will at that moment, okay, so at that moment, the moment we use SBOX, linear cryptanalysis will not work, because so the moment we use SBOX, the cryptanalysis, the linear cryptanalysis will most probably not even work, right? Because take a look at the type of message we will send. I don't necessarily think that they can figure this out, because we are performing so many SBOX and so many rounds. Of course, if you're performing one SBOX, then it makes sense how cryptanalysis will work. But we're using multiple SBOX, so there should be no reason why linear cryptanalysis will work. Its nonlinear structure ensures a low probability of predictable outcome differences for given input differences. Of course, just like I said, if it's one SBOX, then I am pretty sure linear cryptanalysis can itself figure the entire thing out. But we are doing so much things. We are doing add round key, we are doing shift rows, we are doing SBOX, we are doing mixed columns, and we have separate around constants, and we generate new words by performing XORs and many things, right? So there should be no reason why linear cryptanalysis will work. In my eyes, it just breaks down right here. For linear cryptanalysis, the entire thing breaks down right here. Mixed columns ensure diffusion, where change in one byte spread across multiple bytes in the subsequent rounds. Right, so as you can see, this is a matrix multiplication with a predefined matrix. If it was just this, then it makes sense why it can break out. If we only had mixed column, it absolutely makes sense why it would break out. But it shouldn't, because we're doing multiple things, right? So that's the only thing, right? We're doing so much things, and that's the reason why none of these two will work. So in key schedule, round keys are derived through transformations, ensuring unpredictably at each round. As you can see, round keys are derived through transformations. So we're doing a lot of lot of transformations to get each value. So it's not a variable, it's not predefined, it's not constant. That's why none of these two will work. Multiple round AES uses 10, 12, 14 rounds, making it computationally unfavorable to find any useful linear relationships. That's exactly what I said. High diffusion AES structure ensures that even small changes in plain text spread across the ciphertext quickly. Okay, that's basically our comparison. Now we are going to talk about the security strength of AES. Brute force attack involves systematically trying all possible keys until the correct one is found. The attack's favorability depend on the key's length and computational power. Of course, this is true. That's why I said there could be a good chance that we might be getting more bit size for the AES. Probably not, but we might have a more advanced algorithm with a lower bit size coming up. Maybe, I'm not really sure. But for now, our AES is very safe because it's going to take 340 1 decillion to perform all total possible key combination. AES resistance. AES supports key size of 128, 192, and 256. Even with a 128-bit key, total possible key combinations, just as I mentioned, it's going to be 340 1 decillion, and 1 decillion is 1000 times larger than a decillion. Decillion is 10. I'm pretty sure you guys know what decillion is, right? So, and 1 decillion is 1000 times larger than a decillion. At the rate of quadrillion guesses or seconds, it would take billions of years to exhaust all possibilities, far beyond practical limit. Of course, bro. Of course, it's going to take so much long. Even if he gives the task to his next 10 generations, it's not going to be possible. Even after 50 generations, they will not be able to decrypt any of your messages. Classical computers, a longer key exponentially increase the difficulty of brute force attack. AES 128, 192, and 256 provide progressively stronger security with increased computational overhead. Right? Yeah. Quantum computers, yeah, so we're going to talk about quantum computers because they are very fast and they can threaten our systems, right? So quantum computers arise from Shor's and Grover's algorithm. Grover's algorithm can theoretically reduce brute force attack time for symmetric encryption by a square root. So it's a lot, effectively halving the key length. AES 128 would provide only 64 bits of security under quantum attacks, while AES 256 would still offer 128 bits, making it quantum resistant for the future. So as you can see, our standard will definitely go up, or we will have more advanced algorithm that is focused on on blocking the quantum computer out, like making the quantum computer inefficient. The thing is, there is a wrong perception that the quantum computers are good at everything they do. They are the fastest at everything. No, quantum computer is probably even worse than your own computer. You see, that's the wrong perception you have. Quantum computer is worse than your own computer. Quantum computer is only good at one task, while your computer is good at every task. That's why if you make it so that quantum computers have to change between various tasks to decrypt a message, then they will not be able to do so unless they make it so that the quantum computer can do so. But for that you have quantum agility. So what quantum so you have crypto agility that I will explain later. Crypto agility is just like the name implies, being able to switch between these security standards quickly in just a matter of seconds. So let's say I have AES 128 and someone is trying to hack my system, then crypto agility, using crypto agility I will be able to switch it to AES 256 faster. So that's exactly what crypto agility is. And if you have that, then it's not possible. It could be possible, but I think you could make it such that the quantum computers won't be able to break through your defenses. Yeah, AES Advanced Encryption Standard is designed to be highly resistant to common cryptanalysis techniques such as linear and differential cryptanalysis. T2 is structure and design principles. Comparison of AES RSA Cha-Cha-20. RSA is a symmetric algorithm based on prime factorization, while AES is symmetric. RSA requires much larger keys. Okay, that's a lot of keys. That's a big size. 2048 and 4096 bits to match the AES 256. To match the security of AES 256. AES is faster for bulk encryption due to its block-based symmetric design. For Cha-Cha-20, both are modern and efficient algorithms, but Cha-Cha-20 is a stream cipher often preferred for lightweight and mobile applications. AES is more widely adopted and standardized for general use cases. Application of AES is a core encryption method used in protocols like TLS or SSL to secure data transmitted over the internet, such as browsing websites, HTTPS, or online banking. Used in encrypted messaging apps, WhatsApp, Signal, Telegram, to ensure messages, calls, or video calls remain private and tamper-proof. BitLock and similar disk encryption tools use AES to secure data stored on hard drives, preventing unauthorized access. Secure cloud storage services such as Google Drive, Dropbox, OneDrive encrypt files using AES before uploading to protect user data from breaches. Yeah. AES is also used in secure file transfer protocols like SFTP and FTPS, and it is also implemented in IoT devices and embedded systems to encrypt sensitive data transmitted between the devices and the server. Its efficiency in hardware makes it suitable for constrained environments like microcontroller and smart cards. It is also widely used in wireless communication standards such as WPA2, WPA3 for Wi-Fi security. Common attacks on AES and defenses. So side channel attacks. So these attacks export information during encryption, such as power consuming electromagnetic emissions or execution timings, rather than breaking the algorithm directly. So that is what exactly side channel attacks do. And we're going to also talk about what the defenses are. Examples are power analysis, monitors power usage patterns to deduce the key. Timing attack measures the time taken for operations to infer parts of the key. And to mitigate this, randomizing execution times or adding dummy operations using constant time algorithms to prevent time-based inferences, making sensitive computation to obscure power and electromagnetic signatures. And we have fault injection attack. This is another type of attack. Explanation: these involve introducing false voltage spikes, laser pulses during AES encrypt operations to cause incorrect computations revealing key related informations. To mitigate this, we have error detection and correct mechanisms to verify encryption results, hardware level countermeasures such as tamper resistant designs and redundancy checks, ensuring robust implementations to handle unexpected input conditions. And we have differential and linear cryptanalysis. That's exactly what we went over, but this slide is just for an review if you want to go over it. So yeah, and we have future challenges and developments in AES. We're going to talk about the threat to symmetric encryption by the quantum computers. So quantum computers leveraging Grover's algorithm can reduce the efficiency security of a symmetric encryption method by approximately half. AES 128 efficiency security would drop to 64 bits. AES 256 would still provide a relatively strong 128-bit security level. This highlights the need for longer key lengths and exploring quantum-resistant cryptographic alternatives. And that's exactly kind of what I mentioned before. So these are all just like an overview of post-quantum cryptography, PQC. PQC aims to develop cryptographic algorithms resistant to quantum attacks while remaining secure against classical computers. Lattice-based cryptography, hash-based signatures, and code-based encryption are leading candidates in the field. Symmetric encryption like AES is generally considered safe against quantum attacks with sufficiently larger key sizes. But PQC efforts focus more on encryption crypto systems, RSA, ECC, which are highly vulnerable. NIST's ongoing standardization of PQC algorithms aims to replace traditional cryptographic systems in the near future. So they're planning to replace their traditional cryptographic system using the advanced AES techniques and other things. We have hybrid encryption systems. Hybrid encryption systems combine classical encryption with quantum safe and cryptographic algorithm to ensure immediate security while preparing for future quantum threats. So we use AES, quantum resistant with longer keys, alongside lattice-based public key encryption for secure key changes. So that's one of the examples. The importance of cryptographic agility, and this is exactly what I mentioned before, cryptographic agility. So it refers to the ability of a system to switch between cryptographic algorithms easily as threats evolve. Just as I said, secure systems must be designed to upgrade or replace cryptographic algorithms with minimal distribution, integrate new standards such as post-quantum algorithms without requiring complete overhauls. Agility ensures long-term viability and security in dynamic threat landscapes. And that's basically it. D4, thank you. I don't think this slide saved thank you. But yeah, that's exactly that's going to be the end of this video. I am not sure if I will explore DES or the other encryption algorithms mentioned, because I upload topics on what I like on mood. But if you have any questions, do let me know, and maybe comment on what I should improve, and maybe provide a feedback or just something that that was good about me or bad about me, that I can put on my maybe college application or something. But yeah, I tried my best with this presentation. It's actually my first time presenting, so I was a bit nervous. I don't think anybody's going to go through the 130-hour long presentation, but if you do, thank you for watching my presentation. Thank you. Bye.